Okay, welcome. So this is Dr. Morton again, and this is day 18. I'm going to cover chapter 9 today. Let me first turn to the syllabus, and we'll just bring that up over here. So this is October 3rd, Monday. This is week 7. We're really pretty much halfway through the course at this point. And remember, we're going to have the group presentations the week of the 17th through the 21st, so not next week, but the following week. And we probably can do it in 1 day or 2 days at the most, because we just have 4 groups. And I do want you next week to turn in your truth table by Friday, and the turn-in link and all that's available, the description of what you have to do, and your project assignment. So there's groups 1, 2, 3, and 4, and your problems are 1, 2, 3, and 4 on the description of the problems that's in the group project folder. So go to the group project folder, and there's also an example video of a project that some students did before. They used a 7-segment display, not the 16-segment display, but it gives you a great idea of kind of a good presentation. Okay. Remember that there is a homework due on Friday, so for chapter 8. So try and do that. And this weekend, the chapter 9 quiz. All right. So with that, we'll switch to the book. So here's the book, and sorry, it went out. We'll get it here. Okay, so here's the book, and we're going to cover some of the same devices we just covered in chapter 8, only we're going to cover them with respect to how they would be represented in either using C language in our microprocessor or Verilog and programmable logic. So let me draw your attention. So here are the objectives, and I'm not going to go through these right now. Well, I will. Be able to describe 3 major advantages of using hardware description language for design. Be able to write a simple combinational module in Verilog, and explain at least 3 different implications for C++ microprocessor-based solutions versus Verilog field programmable gate array-based solutions. In other words, programmable hardware versus programming a microprocessor. And we'll talk about some of those differences. And then then I'd like you to write a short C program segment and a short Verilog module to implement a 4-to-1 multiplexer. Now, here's the glossary, and I go over all these things, and I spend a lot of time on the multiplexer in this chapter video. So I do encourage you to pull up this chapter video and watch that. I think that will really help you. And I think it's about 40 some odd minutes, so be sure and do that. And I'm not going to repeat the things that this video covers, so you should definitely do this. Okay. What I do want to talk about is I want to give you a little maybe better overview of Verilog and hardware description languages in general. So I'm going to focus a little more on that. Okay, so let's go to the slides. So again, we're going to try and go through here. So these are the learning objectives, which I covered already. So why do we need hardware description languages? Well, I've done a bunch of different examples already, so without belaboring the point, here's another example. So if one of the latest NVIDIA chips has 14 billion transistors on it. So if each transistor took so here's a transistor right there with a resistor, a base resistor, and a diode on the voltage in, okay, or the signal in, whatever. So say this take 1 square inch, that's it, and you have 14 billion of these. That's 3.487 square miles. Now you can make it a little smaller, but really a square inch isn't very big. It's blown up here. So as you can see, there's no way to have a 3.5 square mile schematic. It's just not possible. So we have to use layers of abstraction and higher level. We have to use these English language based descriptions, in order to have even a chance of designing something like this. All right. So too complex to do the design with the schematic. We can't work at the transistor level. We need to work much higher, and we need to let computer-based tools work at the transistor level. There's a lot of tedious work involved, and we need the computers to do that, not our engineers. So that's why we need hardware description languages. But that's not really how they came about. They came about in a little bit different way. They really started out in two different main languages, Verilog and VHDL, and they both VHDL started by the Defense Department, and it came from a language that they used that they required their primary contractors to use, called Ada. And originally, VHDL was just created to document the program that had been written in Ada. And then over time, they realized that they could actually use it to simulate some things. And then finally, they realized they could actually use it to synthesize hardware. And that evolution took a period of time. And Verilog went through something similar. Initially, more for documentation, and then eventually simulation, and then synthesis. And they both become IEEE standards. In the last several years, we've seen additional languages now come forward, mostly along the lines of System C and System Verilog. These are really extensions of Verilog. So learning Verilog is still really essential, because these other languages also use Verilog, but they bring with it the features from classes, and so that's really the main difference. And I think you will see a move to Verilog. To System C or System Verilog. I'm not sure which one's going to win. They'll probably sort of merge into the same thing. So hardware description languages have features which allow you to describe some of the behaviors of electronic components. The main feature that they bring is that they allow you to describe the time considerations. So both we talk about propagation delays, the time it takes for the circuit to change from one state to another. In Verilog, we call that the inertial delay. And then we also need to model delays that have to do with the length of time signals take to move along a wire, and we call that a transport delay. And Verilog makes a distinction between these because they have a different effect on simulations. We can describe things from simple sets of logic gates to complete complex microprocessors. The latest Intel and AMD chips are described in Verilog, maybe System Verilog by now, and that's how they're put together. It's very complicated, and the only reason that these things are able to really be created is because we have these computer-based tools. And again, the electrical aspects of these circuit elements are also described. We can describe rise times and fall times, delays through gates, and all sorts of things. VHDL is one of the main HDLs, and again, I mentioned it came from the DoD and Ada, starting in the early 80s, and it's involved into IEEE standards. Verilog is another, and this was originally created by Gateway Design Automation and then purchased by Cadence Design System in 1985. And then in 1995, they allowed it to become an open standard, and it became an IEEE standard then. It comes from the C language, and that's why it looks a lot like C. And it's really used more in the USA for integrated circuit design than VHDL, but you will see both. And in Europe, you'll see a little more VHDL. In this department and in this course, we're pretty much use Verilog, or System Verilog, or System C. So you can see these here. I'm just comparing them side by side. So Verilog it's a hardware description language. So is System Verilog. System Verilog can be used to do structure and model, to design and model electronic systems, and System Verilog can use that too. It's maybe a little more efficient for larger systems. This supports structured paradigms. This supports structured and object-oriented paradigms. So it has the object-oriented features built into it. It's based on a module-level test bench, whereas System Verilog is based on a class-level test bench. And there are different IEEE standards. And Verilog is influenced by the C language and Fortran programming, whereas System Verilog was based on Verilog, VHDL, and C programming. The extension for Verilog is .v or .vh, and for System Verilog it's SV or SVH. So Verilog supports wire and register data types, but System Verilog also supports those plus enumerations, unions, structures, strings, and classes. In Verilog, it's based on the hierarchy of models. You have a top-level module of modules. You have a top-level module, and then you have submodules, and many of the submodules have submodules as well. Whereas in System Verilog, it's based on classes. And again, it was originally intended as an extension to Verilog in the early 2000s. So C, C++. So an awful lot of digital logic is created using embedded processors and C or C++ to program a microprocessor. And the distinction between a processor core and say a programmable logic circuit is getting a little bit fuzzy because many microprocessors have some programmable logic blocks included, and many programmable devices like FPGAs have built-in microprocessor cores as well. Sort of driving this fusion is the fact that complex problems often take a mixture of parallel and serial algorithms. So some algorithms work really well in a stepwise manner, step 1, step 2, step 3, and some where you have multiple things happening all at the same time, so-called parallel algorithms. And it turns out that a computer core is really good at doing things in a serial fashion, and programmable logic are application-specific integrated circuits are good at doing things in parallel all at once. So what's the difference between Verilog and C++? Well, one creates logic and one runs on an existing logic device. So C++ runs on a core that's already been built, whereas Verilog is actually creating logic, including it can create cores. All right. So they're still growing in usage, and they borrow most of the features from Verilog. So learning Verilog is still important to understand System Verilog or System C. Okay, so hardware description language simulation models can be used for building blocks in larger circuits, and we can use them to simulate, which is really important when you're making an integrated circuit. You want to get it right the first time. So what you do is you're really careful to have lots of checks at every step and to simulate everything to make sure that the timing's going to work and that the logic is correct. And so the simulation is a really important feature of the hardware description language. It also, of course, allows us to synthesize the circuit we're creating. And we can do that in the form of a bit file that goes into programmable logic like an FPGA or a CPLD, or we can use it to generate all the photomasks and steps in the foundry to actually fabricate an integrated circuit. So hardware description language are also general purpose programming languages. This allows us for very complex systems, allows for events that happen simultaneously to be described. And it can capture the performance specification for the circuit in terms of its timing. Within that, we always should have a test bench, which basically does the simulation. And the same engineer that sets up the Verilog code is also the one that will do the test bench, or the same team typically. And that test bench then should be built to as much as possible fully exercise the design and make sure that the simulation verifies both the logic, what it's supposed to do, and the fact that it's going to do it in the time frame that was targeted in the original design specification. So we do use the measures of propagation delays and inertial delays and transport delays that are described in the code to do these simulations, which hopefully give us a realistic picture of how our actual hardware is going to function. All right, we normally talk about different levels of abstraction, and we have at the top level we have a behavioral description, which might be S equals A plus B, and then we might describe the data flow in terms of how many bits we're going to have, what registers we're going to use, and then at some point we may actually have a structural description where we describe how the gates are going to be set up. Are we going to use AND gates, OR gates, exclusive OR gates, how many layers, how is it going to actually be done? And then finally, we either generate a bit file and program a device, or we generate all the tools to go to the foundry and make the integrated circuit, and we wind up with a physical implementation. The physical implementation, of course, is no longer a hardware description language. It's a real thing. We don't have to throw away older design work because as synthesizers improve and the language develops, the old code is still workable, and the tools get improved, but the code can still be fine. Just the old code can work just fine, and it's a good way to share knowledge with other designers. And there's currently a very large ecosystem of existing intellectual property that can be used to really quickly get to a complex design. So here's a simple circuit, and I'm going to describe this in VHDL and Verilog both, but again, we're really not going to focus on VHDL, we're going to focus on Verilog in this course, and in the ECE department. We pretty much do Verilog. So here we have an AND gate with inputs A and B, and then the output of that AND gate goes into an OR gate that also has another input D, and it gives an output of E. So in VHDL, we would write this: the signal C is assigned A ANDed with B after 5 nanoseconds, and E is assigned C ORed with D after 5 nanoseconds. Whereas in Verilog, we would say assign C #5 equals A ampersand B. So this is more, the ampersand would be C syntax for the bitwise and this would be the vertical bar would be the syntax for the OR gate. C ORed with D, again bitwise, but since they're individual bits, you could use the logical or the bitwise. So there are 3 different ways to model this 2-to-1 multiplexer. So this is a simple circuit. Okay, so we looked at it in VHDL and Verilog, but now we're just going to focus on the Verilog. But notice how this is very much, except for this #5, this is C syntax. Now, this #5, or this after 5 nanoseconds, that's where we put in the timing delays associated with this gate. So we would try and pick these numbers to be close to what we'd expect our final hardware to actually do, whether it's a FPGA or whether it's a brand new integrated circuit. All right, so 3 ways to model a 2-to-1 mux. So one way would be to set it up like this. We have a port list. So whenever we do write Verilog, we always do it in a module. So here's our module keyword here, and our end module keywords down there. Then the name of this module is mux4, and it has a port list of I, A, B, and F. Now we don't describe whether these are inputs or outputs here, but we do here. So A and B are inputs, and if we don't specify register, then we assume they're wires. And here we have an input 3 to 0 I. So what this is a vector. It's also a wire. And then finally we have a single bit output F. So this I is a 4-bit vector. And that's, of course, the input to the multiplexer. F is the output. And A and B are the control lines. And here you go. We write assign F equals not A ANDed with not B ANDed with I0. Or not A ANDed with B ANDed with I1. Or, and essentially this works out to be, let me just show this on paper. So essentially what we're doing here is, so here's our multiplexer. Here's our output F, and here are I0, I1, I2, and I3 inputs, and our 2 control lines, A and B. Okay, so what we're saying is F equals, if A and B are both 0, so that's A prime, B prime, I0, or A prime B, I1, or A B prime, I2, or A B, I3. But we're writing it in Verilog, where we have to use an ampersand for our AND gate here. So we have to put an ampersand in for each of these operators, and then we have to use, instead of A prime, we write not A, ampersand, not B, ampersand, I, and then we use the Verilog notation, square brackets, and so forth. So that's why it looks funny, but it's the same thing we've done before. All right, and then we have end module. So that's all there is. We do follow each statement with a semicolon, just like in C. This is one continuous line, so we don't put a semicolon until there. And then we have the end module statement. Now, in this case, we didn't have any internal signals that didn't show up in the port list. These variables are just, the variable names are local to this module. But they connect through the port list to the outside world. And if it's a top level module, then it actually does connect to pins on say the FPGA or the integrated circuit that we actually create. If it connects to other modules, then we instantiate it in those modules, and it may or may not communicate to the outside world. Depends on whether it's connected to that module's port list. All right. Another way to do it is this mux4 like this. So we have mux4, I, A, and F. B should be up here too. I don't know what happened to B. Yeah, that's a mistake. Let me fix that real quick. Okay, I can't fix it real quick because it's a picture. So I have to do this another time. But anyway, so we have inputs A and B. Those are our control lines. We have a vector, a 4-bit vector I. That's I0, I1, I2, and I3. And we have an output F. So I and A are inputs. F is the only output. And we only know this because we specify this down here, which is just, it's part of the port list. But we write it, we put the variable names up here, and then we describe them here. And then assign F equals, now this is the conditional assignment operator, and we have 3 examples of it, okay? We have F equals A question mark, and then in parenthesis, if A, so we evaluate A. If A is true, then we take this. If A is false, then we take this. So what happens is if A is true, 1, then we take this, and if B is true, then we take I3 equal to F. If B is false, we take I2. On the other hand, if A is false, which means it's equal to 0, then we take this, and if B is true, we take I1, that would be A prime B, but if they're both false, that would be A prime B prime, then we take I0. And that's how we get all 4 selections. We use this nested assignment statement. It'd really be wise of you to get smart on this. Again, let me just take a second and draw this out. Let's see, I'll do this. So remember, the conditional assignment looks like this. Our output F equals our first signal. We're going to test A, and if A is true, then we have this question mark. We're going to do this, whatever it is, and if it's false, we're going to do this. In this case, we put a second conditional assignment in here with B and a question mark, and I3, I2, and we did the same thing over here, also with B and a question mark, and I1 and I0, and then we finish it up with our semicolon. All right, so hopefully that makes some sense to you. All right, so let's go back here, and then the final way we're going to do it is we're going to use an always block. Now, we haven't looked at always blocks yet, but let's see. I guess you couldn't. Let's see if you can. Maybe. Let's see if I can do the. Well, okay, never mind. I'll let you see this over here. I guess maybe you couldn't see it. Anyway, so the always block allows us to use some fancier stuff. Normally, an always block is for sequential logic, but you're allowed in Verilog to use it for combinational logic. And what happens is the synthesizer is smart enough to know you really didn't intend this to turn into sequential logic, so it converts it to combinational logic. But you're allowed to use if statements, while statements, case statements, and other things in here, which you can't use outside of always blocks. But when you use whatever's on the left-hand side, in this case F, it has to be a register. Now, in this case, it won't be actually a register. It will be. It has to be a register for this to compile correctly. But the synthesizer will convert it back into a wire because it knows what you really intended here was just a combinational device, a multiplexer. All right, but you can see. So if A and B, then it's I3. So if A and B are both 1, I3. Else if A and not B, I2. Yes, that's right. Else if not A and B, I1, and else if not A, not B, I0, and module, or end always block and module. So very similar, but 3 different ways to do exactly the same thing. And this takes about 10 nanoseconds to execute in a typical FPGA or typical integrated circuit where you might make this. So it's going to be fast. Now, what if we did this in C++ in a microprocessor? Well, we could write it like this. We could say assign some of the ports, say bits 0, 1, and 1, 2, 3 in port A, 1, 2, 0, 1, 2, 3, and an output bit 4 for the output, and then use port A bits 5 and 6 for the 2 control lines. And then you could write while 1. So this is an infinite while. We're just going to execute this over and over. Now, we wouldn't normally just do this. That would be a pretty minimal use of a processor, but in theory you could. And we'd say not PTA and not PT6. If that's true, then PT4 equals PTA 0. That would be I0. And again, PTA 4 is our output F. So this is basically F equals I0. And then this is if A prime B, so that'd be I1, this would be I2, and finally else I3. So With a processor running at about 32 megahertz, the execution time would be something like 6 microseconds. Now, the problem though is, if all you did was execute this loop, then your microprocessor could be turned into a multiplexer with a propagation delay time of about 6 microseconds. That's opposed to 10 nanoseconds. So it's still going to be almost a 1,000 times slower. But it's even worse if you do other things with your microprocessor and only every now and then execute this. Because remember, in a microprocessor, you're not doing all your lines, all your program lines are not being executed simultaneously. They're being executed one at a time in some sort of pattern based on loops and things like that. Whereas in programmable logic, when we make two different gates, they are executing simultaneously all the time. Anytime you change a right side signal, the left side will be reassigned. And they can execute concurrently. So that's the big difference. So if that were the case, and you were out doing a bunch of things, you might have many seconds between execution of this. So it might actually be seconds and not microseconds, and certainly nowhere near nanoseconds in its responsiveness. So the chapter video goes over this, I think, in pretty good detail. But these are the rules for identifiers in Verilog. Generally, they're case sensitive. They can include letters, numbers, or special characters, of which there are two, the underscore and the $sign. They have to begin with a letter or the underscore. They cannot begin with a number or the $sign. They can be any length from 1 to 1,024 characters, but that is the maximum length. They cannot have any spaces, and they can't be reserved words like module, assign, end module, and things like that. Okay. And then I went over constants pretty thoroughly in Verilog in the chapter video. So please watch that. But let me just we'll just talk about this real quickly. When we write constants in Verilog, we write them in a really funny way. So we would say A equals, let's say A is a single bit. Then it would be 1 tick B 0. So that assigns 0 to A. Now you can also write A equals 0. But this is how it likes to see the constants. And so this is the number of bits, then there's a tick mark, and then there's the base, which is either B for binary, D for decimal, H for hex. Those are the main ones. There's also O for octal. And then you have the digits. Generally, like for instance, let's say you did, let's say A is defined as a 4-bit vector. So we set it up, assign, let's see, 3 to 0 A, and we set that equal to 4 tick hex, not B but hex. Then you can have like A. So that then A would equal 1010. And it would be 4 bits, 1010. Or you could make this F, in which case it would be 1111 or whatever. So you get one hex character. Remember, this number before the tick is always the number of binary bits. Okay. All right. And I'm not going to spend much time, but it does get very complicated. They can be signed. We also have some extra things we can put in, like where we use our 3-state buffers. We can have a high Z state. We write that as a Z, and we can also have an unknown value, X. And here are all the operators. This is very similar to C, and I went over this in fair detail in the chapter video, so I'm not going to repeat that. Here's our exclusive OR gate again. This is the 2-input one. If they're both 0, you get a 0. If they're both 1, you get a 0. And if you just have 1, 1, you get a 1. Remember, if you have 3 inputs, what happens if you have 3 1s? You get a 1. All right. So here's a little simple Verilog code example. we have E equals A ANDed with B, F equals C ORed with D, and G equals E ANDed with F. And here it is. So I didn't put the E and G on, the E and F on, but this is E and this is F. And then the output G. All right, 4-bit adders. So we can do 4-bit adders a couple of ways too. We can make a 1-bit adder, and I did that right here. So this picture has 2 modules in it. The first module ends here, and then we have the second module that ends there. The second module is a 1-bit adder. 1 bit of X, 1 bit of Y, 1 bit of carry in, and an output of 1 bit of carry out, and 1 bit of sum. So that's a full adder. 3 inputs, 2 outputs. And we instantiate this module here 3 times in this top level module. And we have in our port list A and B, a carry in, a carry out, and a sum. Notice that A and B are both 4-bit vectors, and our carry out sum is a 4-bit vector, and they're all wires. And then here's how we do. We instantiate 4 copies, and we just make sure we put the right things in. So when we instantiate this, 2 things. We have to give it a unique name. In this case, we call it N1 for instantiation 1, N2, N3, and N4. We have to use its unique name, add 1. So there it is, add 1, instantiation 1. And then we have the port list. Well, notice the port list has to be in exactly the same order here. So if X is going to line up with A and B is going to line up with Y, the carry in with the carry in, the carry out with the carry out, and the sum with the sum bit. So we do A0, B0, carry in, and then we have these 3 internal carries where we're passing the carry. So let me just show real quick. If we look at this with 3 modules, or 4 modules, so here's our 1-bit adder, okay? Just like we did in the last test, we have 4 1-bit adders. So we have 1 bit of A, we call it A0, 1 bit of B, B0. We have a carry in. These are inputs, and we have a sum out, sum 0, and we have a carry 1 out. And then this becomes the carry in for this next 1-bit adder. We put in B1 and A1. I wrote them the other way here, sorry for the confusion. And we have a sum 1 and a carry out. We'll call it C2. And finally C3. And finally the carry out from the whole thing. And this is sum 2. And this is sum 3. And this is going to be A2, B2. And this is going to be A3 and B3, just like we did on the last test. So we have 1, 2, 3, 4, 5 outputs, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9 inputs. Our carry in's an input, but these internal signals only show up inside our module. You can see they only show up in here. They're not part of that port list. So the outside world can't see these signals. And all we have to do is make sure that the carry out from the first instantiation is the carry in, and the next, the carry out from here is the carry in, the carry out from here is the carry in, and the final carry out is the C out that does appear in a port list that comes out from the entire 4-bit adder. So hopefully that gives you a little bit of an idea of how that works. Okay, now we can also do this another way. We can just write A plus B plus carry in equals carry out comma sum, and we concatenate these to give us a 4 bits of sum and a 5th higher order bit of carry out. And we use the concatenation operator to do that. And again, port list, all the same. And here the synthesizer does all this work for us automatically. And in fact, it might not even use a carry ripple adder. It might even use a fancier adder. It might use a carry propagate or a carry look ahead. All right. If we wrote this same thing in C for a microprocessor, then, well, we'd say sum equals A plus B plus carry in, and the carry out equals C, where C is the carry status bit. But the sum would automatically include that because we'd be using integers here, and it would just already have the whole sum here. 4 bits of sum plus the carry out. All right, so you can see this is nice and easy on a microprocessor. It's a little more complicated on programmable logic. All right, ROMs and Verilog, also very easy to do. So we just declared register 7 to 0, so that's an 8-bit word, and we're going to have 0 to 31. We're going to have 32 of them. Now, why do we write this 7 to 0 and this 0 to 31? Well, it's because we normally think of our bits left to right, the higher order bit being the leftmost bit, and the lower order bit being the rightmost bit. Whereas if we have 32 of these, we just think of row 0, row 1, row 2, row 3 to row 32, or row 31 rather. And that's all it takes. And then let's say we wanted to set the 8 bits of row 12 equal to, say A0x A5 in hex. We just do 8 tick B 1 0 1 0 0 1 0 1, and that would do the job. Now, when we write this, the synthesizer automatically creates all the flip-flops required to store all the data of the ROM. Now, how many flip-flops does it take for this? Well, how many flip-flops are required? So you have each row is 8, and you've got 32 rows, so that's 8 times 32, or 256 flip-flops to hold the information. And how many address lines would it take for this? Because we didn't really describe, I didn't really do an entire module here. So our address lines, how many would we have to have? Well, our values are 0 through 31. So we basically need 2 to the 5th, because 2 to the 5th equals 32. So we need 5 address lines. All right, so a few sort of last points. So we've covered how to write variables. We've talked a little bit about wires and registers. I haven't said much about registers. That'll come up later when we do the sequential part of our hardware description language, where we use always blocks to make things like flip-flops and state machines. But our variables are case sensitive, and the name is local to the module, and the variable is local to the module too, unless it appears in the port list, and then it can connect to the outside. We don't necessarily, the name doesn't connect to the outside, but the value of the variable does. We've only covered combinational Verilog, so we are going to get around to sequential design for Verilog. State machines always require always blocks, and we're going to cover that. And remember that Verilog turns into hardware, but your C++ programs existing hardware. But there's lots of crossover. We have microprocessors coded into our programmable logic, and we have embedded controllers that have programmable blocks built into them. So we see these things really colliding. All right, that's pretty much it. So be sure you look at the video, the chapter video. Probably should do that first if you have, I guess at this point you've already looked at this video, but go back and look at the chapter video if you haven't done that. And that'll do it. We will see you then on Wednesday in class. Remember to come to class on Wednesday. There won't be a video.